In the previous part of this lecture, we discussed simple bus operation and showed APB. Now we'll go over to some higher performance buses. So how do we increase bus performance? The APB example is a simple low performance bus. It was used to control peripherals and very slow things. It took 2 cycles to carry out a single transfer. Each transfer required the definition of the address and data, and that was done in 2 separate phases. This can easily be improved just by pipelining the transfer. We can overlap the setup and access phases and therefore achieve a single clock edge transfer. We can also apply burst operations where we provide a single address and multiple sequential data, and therefore we don't have to keep on telling us what the next address is. And we can also support wider bus widths, such as 64-bit, 128-bit, or wider, which in APB was not possible. So we take the next stage of the AMBA specification, which is called the Advanced High Performance Bus, or AHB. So this is the higher performance bus that was initially provided by the AMBA specification to do a bit better than APB. And we can see a general sketch of the APB type of approach, where here, instead of P being the names of the different controls, we have H for the H in the AHB. So in this case, we're looking actually at AHB Lite, which is a light single master type of flavor of the AHB bus, but it's the same basic concept. So we have a single master, and it has, the control data and address channels of its bus. And what we actually do is we provide the address over here, and using the address, we use an address decoder that sees which slave we're actually selecting, and that sets out the H select, which selects the actual slave to work similar to the P select that we had in APB. Okay. Besides that, the data and the control are sent to all of the slaves, but only the one that the address decoder selects will actually operate. The response provided by the slave will go to a multiplexer, and the multiplexer will actually go and only take one of the responses and pass it back to the manager. So we have the read data from all 3 of them, but we only want to use the one that was actually selected. So again, the address decoder will select which channel of the multiplexer will go back to the master. And same with the response, which will be kind of the ACK of the slave. So how do we do that? We have a master interface and a slave interface, and we see some of the signals, most of the signals over here that are, again, symmetric and that go to the master and the slave interfaces. So let's see how a basic AHB read operation occurs and how it actually gains more performance over the APB. It has 2 overlapped phases. So in the address phase, the master drives the address and control signals onto the bus. So we have the H clock over here, and in the first phase over here, the control and the address for the first transaction are put on the control and H address signals. Okay, what happens is that similar to before, once we have the rising clock cycle, we have a cycle latency, and the slave will provide the read data on the HR data bus. However, at the same time that that's happening, we don't have to go and wait for an enable and then provide the next control and address. We can already overlap this and provide the next control and address on the control and address buses driven by the master. And therefore, we can already receive the next read data on the next clock cycle. So that's how we overlap or pipeline the different signals, and we're able to get double the bandwidth that we could get with APB. In addition, we have, as we mentioned before, burst transfers. So burst transfers are supported by AHB by giving us different burst lengths. The master provides an address, and it provides the burst length. And then we can apply several read or write operations to incrementing addresses, and this reduces the overhead of the address phase. So let's see an example of a 4-beat read burst and also show how the wait state works. So here we have some of the signals that we had before. The green ones are driven by the master. The red ones are driven by the slave. Okay, and so what we'll start with in the first cycle is that the master is going to provide the address, and it's going to say what it's going to say that this is a read operation by lowering H write. And in the meantime, it's also going to tell us what type of a burst it's going to be in. And it's telling us we want a 4-beat read burst, and it's going to use this H-trans encoded to non-sequential. That's just how the protocol tells us to start a burst. Okay, on the next cycle, what we're going to have is, since we provided the first address, the slave is going to respond with the HR data. It's going to say what the data was. But actually, the master decided over here that it's not actually ready to receive the next address after this. So it can change the H-trans from being non-sec as it was here. It's supposed to change into sequential. It changes it instead into the busy encoding. And that actually incurs a wait state. So we're not going to get read data on the next cycle after this. So in this next cycle, even though we did increment the address, the slave is not going to respond with the data from the previous one because the master said it was busy, and so it's not ready yet to receive this. But in this cycle, now the master changes this H-trans back to sequential, which means it's continuing with the burst. And therefore, already in the next cycle, we are going to get the read data from the address that was incremented from before. And so that is the second basic data that we get. We continue over here and we get the third data, incrementing the H address and providing the data. But at this point, now the slave says it's not ready anymore. It wants a wait state. It's going to take it longer to go and handle the next transmission. Maybe it wanted to get a cup of coffee or something. So it lowers the H-ready signal over here. And that therefore we have basically a dead signal over here where everything is waiting and the master is keeping its signals stable. Finally, the H-ready is raised again, and on the next clock cycle, the read data is supplied to the read data bus, and we have finished our transmission. So AHB also, as opposed to APB, can support multiple masters. So if we have several masters over here that each have their address and data buses that they're driving out and the read data that's coming back in, we add the arbiter over here to the equation. And basically, there are multiplexers for the address and the data, and the arbiter decides which of the masters actually get to send their data and their address through these multiplexers. So that's one thing the arbiter does. And then the decoder helps us to take the response that's given by the appropriate slave and drive it back to the masters, which the master that actually was granted access knows that it's supposed to use it. But maybe we want to get even more performance. And to do that, we can add the bus, we can add a few capabilities to the bus. We can have independent read and write channels. If we have independent read and write channels where they don't use the same channel, we can have simultaneous reads and writes, and that really can improve our bandwidth a lot. We can have multiple outstanding addresses. Who said that the master has to, set up an address and then immediately wait until the slave is ready to respond? Maybe it can send several different transactions to different slaves and so forth and have multiple outstanding transactions on the bus. What about out-of-order transaction completion? Who said that a certain transaction has to complete before the next one that was transmitted complete? So that's another type of thing that can make things work a lot faster and very complex and buses with many components on it. And we can have independent address and data operations. If there's no strict timing relationship between the address and data operations, they can be arbitrarily separated. You can say, okay, this is my data, and now that's the address, instead of saying this is the address, and now that's the data for it. In order to do all of these things, what we need to do really is provide an ID for each of these transactions, so we know which transaction the different address and data and ACK phases are talking about. And so that what is implemented inside the AXI, or Advanced Extensible Interface bus, which is the even higher specification of the AMBA bus. So let's look a bit at AXI. AXI is an interface specification that defines the interface of the IP blocks rather than the interconnect itself. It supports multiple masters or managers and multiple slaves or subordinates. and it uses 5 main channels. And when we say a channel over here, it's not just talking about a signal like a 32-bit signal for the address and a 32-bit signal for the data, but rather a whole channel that has extra control signals and so forth inside. Specifically, we'll be discussing it has its own handshaking for each of these channels. So what are the channels? We have the write address, write data, and write response for writes. So if we have the master and it wants to initiate a write, what it's going to do, it's going to use this write address channel. And again, this is a whole channel with control on it, okay? It's going to put the address and control of the whole transaction onto this, do a handshake and so forth. That's going to be sent to the slave. It's going to put the data on a separate channel. And again, you can see here it's a burst, so it's putting several data for the same address. And then for the ACK, the slave is going to have this write response or B channel where it's going to respond and ACK that the write was successful. Okay, and we have the read address, which is the read address and read data for making a read operation. So here, again, there's a whole channel with a whole handshake on it where the master puts the address in control and the slave can reply with, in this case, a burst of read data on a separate channel. And here you see we do not have a read response channel, and the reason is that it can encode the ACK onto the read data channel because it has this reply type of a direction that it can talk. So let's see something about the channel handshakes on AXI. So each and every one of those 5 channels has a handshake in it, as I mentioned before, which means they have a valid signal and a ready signal in each of those 5 different channels. The valid signal will remain high until the ready signal rises. And so we can see it's something like this. So we have the clock over here, and we have the information. And once the master actually it's not the master, it's the source, because if we're having a channel that's going from the slave to the master, then the slave will be the source and the master will be the destination. So the source gets the information ready and then raises the valid signal saying that, this is an ACK, I'm ready to send this information. And on the clock cycle, the slave will say, okay, I am ready to receive it. Actually, that's not 100% true because the ready can be asserted before the valid. So it is not dependent on receiving the valid to say that the destination is ready. And we'll see that in a minute in actual waveforms of how this works across a transaction. Okay, so once both the valid and the ready are up, we can go on and on the different clock cycles do the passing of the information, and we'll see how that exactly works. And once this is finished, the valid is going to go down and the ready is going to go down, and this shows that the transaction is complete and we can start a new transaction. Note that ready and valid can both go down separately in order to initiate wait states for both the master and for both the source and the destination. So let's give an example of a write transaction on the AXI bus. So we'll start with the AW channel, which is where the write address is provided. And in this case, we provide the address handshake on the channel. So first, the master comes and puts the address on the channel and raises the valid signal. And that means that it is ready for the slave to accept the address. And then the slave will raise the ready signal saying it took the address. And now both of them can lower the valid and ready signal saying that this transaction was finished. And now in this case, actually a transaction with a certain ID and a certain address was passed from the master to the slave. So the slave knows that that it's waiting for the data for that transaction ID. In this case, the slave went on the W channel, which is for the write data, and it just raised W ready without waiting actually for the W valid of the master. So the master puts the data on the channel and raises W valid. Okay, so that is the handshake between the master and the slave over here. Now, this is a burst transaction, so what's going to happen is after the next clock cycle, when we know now, because this was ready, that the data was received and is being taken care of by the slave, it doesn't actually have the transaction finish and the valid and ready go down. Instead, we keep the valid high and put the next data, which is the next sequential address, on the bus. So on the next clock cycle, on the next rising edge over here, now we know that the slave, which stayed ready, was ready to accept that. But here the master, for some reason, was not ready to put the next data that's supposed to go in the next address on the bus. So it lowered the valid signal. And now the slave knows that it's not supposed to do anything until the valid signal goes up. But it also knows that it hasn't yet finished this burst operation because it hasn't been told that it's finished. And so over here, the master goes again and raises the valid signal with the new data, which the slave again knows that at the next sequential address, it is supposed to now write the data in. And so it accepts that. But at the same time, there was a W last signal, which goes and rises. And that means that it's the final data in this burst. And so that is the end of the transaction. And W valid can go down. And so can W ready if the slave wants to lower it. Okay, but now after the transaction is finished, once the write has been taken care of on the side of the slave, it has the B channel, which is where it responds to, and has to acknowledge that this was done. And so there is this response handshake where basically the slave is now going and raising the be ready signal. So what is interesting about that is over here, once the last signal was raised over by the master, then the be ready was raised by the master saying, now I finished my transaction. I'm waiting for you to acknowledge that you finished the write on the slave side. So the slave, which is now the source of this operation, it actually only finishes on the next clock cycle and then raises the be valid, and then they both can finish and finish the handshake and finish the transaction. So it's the cool thing about AXI is that you can do all those strange things that I said before about transaction ordering. So it supports interleaved and out of order transactions. Let's see a simple example of an interleaved transaction. So here we have transaction A, and we put the address over here in this clock cycle. And then after that, we put the data over here, and we wait until we get the response. So that is all really happening in order and everything. But at the same time, since we have a separate read channel, the master can actually ask for an address to be read, and the slave or a different slave can respond, and that is interleaved with the same write transaction that was going on at the same time. Okay, and again, we can have the second transaction, the second write transaction done over here. We could provide the right address and the right data at the same time. They didn't have to be delayed from each other. We could have some wait states in between and not provide all the right data one after the other. And the actual acknowledgement by the slave could also be delayed. And at the same time, again, we could have another outstanding read transaction happening at the same time. So this is interleaving data. But still, everything is in order. If we want a more complex type of a transaction, we can see kind of strange things over here. So now, in this case, the master is putting the first address number A and the second address number B before he is even finished driving all the data onto the data bus. Okay, and so over here we get the acknowledgement that this is finished, but the transaction is finished over here while B is still in the pipe. And in the meantime, we also asked for address C and address D to be read out, and C was read out, and then D was read out over here. So there's a more complex kind of out of order type of transaction. So now that we've talked about APB, AHB, and AXI, we can discuss the concept of multi-level buses that I mentioned in one of the earlier slides of this lecture. So a microprocessor system can often have more than one bus. First of all, there's an issue of complexity. High-speed buses, as we saw for AXI, they're very complex. They're wider, they have sophisticated protocols. It's really hard to design them, verify them, and so forth and so on. So we don't often need that for simple and slower devices. The other thing is for parallelism. If we break up the bus, we can provide less contention between devices that operate independently and have different transactions happening simultaneously. So a bridge is the unit, as we mentioned before, that connects two buses. So in this little diagram over here, we have a CPU that is connected to a high-speed bus. And often memory or other high-speed devices, maybe a PCI Express or something like that, would want to be on this high-speed bus using something like an AXI. So they're going to be on the high-speed bus. But we have all kinds of low-speed devices and peripherals, maybe a UART or something like that, that really don't want to go and implement this really crazy AXI type of an interface and so forth. So they just interface with an APB slave, and we need to translate between them using a bridge. So the bridge has an AXI slave on it on one side and an APB master on the other side. So it will accept the transactions in AXI. It will go and translate them into APB transactions, and as a master, it will go and send and receive these transactions from the low-speed devices, and if needed, it will respond to the CPU with the AXI type slave on the other side. So this provides protocol translation and speed synchronization. So with the AMBA multi-level approach, which is basically what I described before, AMBA really provides this thing where we have the high speed, it would be an AHB or AXI or something like that bus, which is connected to, you know, their ARM processor or some other processor. It could be RISC-V or anything else. We also have, you know, the high bandwidth memory. We might have a DMA, which we'll be discussing next week, and we'll have high bandwidth on-chip RAM. And then we'll have this bridge in the middle that will translate between the high-speed bus and the low-speed APB bus. And there we'll have different types of things like timers or UART or keypad or all kinds of other things like that. So this is a type of a multi-level approach that AMBA supplies to us. And if we take the Pulpino architecture, which is a very well-known open source program by the Pulp guys at ETH Zurich and at University of Bologna, and we have been using them using our Pulp NX architecture that we use inside the NX labs. So you can see here that they have their different cores that they use over here, their open source RISC-V cores, and we have the tightly coupled memories around them, but our main bus is this AXI4 interconnect. So we have this AXI, which you can also connect things to, but then they have a bridge that goes from AXI to APB, and all of the slow things like the GPIOs, UART, and so forth are going to go through this APB. So this is a very common type of a multi-level approach. So that is all for this lecture, and there are many references over here that you can look at, and I took things from many different places. So I hope you enjoyed, and we'll be discussing off-chip interfaces next time.